So the point I'm trying to make here is that we don't have to make a completely naive search of all the triples A, B, and C in order to find the smallest solution where A, B, and C add up, the fourth powers add up to another fourth power. There's various shortcuts we can make, and this is the point of Fry's work. So essentially, there's lots of things you can do along these lines. And so we've seen that by looking at what happens mod 5, we can see that precisely one of these numbers is not divisible by 5 and the other two is divisible by 5. So we'll make the assumption now that it's the first one which is not divisible by 5 and the other two are. And we can keep on going like this. We can, for instance, we can see that this number is not cannot be even, and various kinds of things along this line, along these lines. Actually, you know, if you want to do this um, mod p for other primes, it gets complicated. So let me just show you what you could do for p equals 13. So, and I'm going to do it in Maple because, as I said, this is much more complicated than the little observation we did mod 5. So what I did was I used Maple to find all the solutions to a to the 4 plus b to the 4 plus c to the 4 is d to the 4 mod 13. So I'm assuming that a, b, c, and d are remainders mod 13, right? So these are numbers between 0 and 12. And this is a long list of solutions, but they all look like this. I mean, I could take all the numbers to be 0. I could let c equals 1, d equals 1, and so on. And I will manipulate this list in order to get the data out that I want. And let me spend a little bit of time on explaining how that goes, because it's various applications of the map command, which is a little bit um, tricky to use. So let's spend a little bit of time on that. So I'm never going to show you the whole sols because it's big. It's like almost 1,300 entries. So if I print it out, this would be several screens. So I'm keeping it in the list, and I'm just showing you the 5 first entries in all the examples. So the next thing I'm going to try to do is I'm going to, oh, I guess we didn't need that. I'm going to make a substitution where I extract the C and the D values, because those are the only ones that I care about right now. So that's done by this map command, and let me explain how this works. All the entries in sols is a set of equations of the form a equals 0, b equals 0, and so on. I want to extract the value at C and the value at D. And I'm going to do that by taking a little vector and write C in the first entry and D in the second entry. And then I'm doing the substitution of, for instance, what I have up here into that. So when Maple sees it, it will say, okay, I know C equals 0, so I need to write 0 here. And I know D equals 0, so I need to write 0 here. Right? So you can see this is a way of extracting those two data and put them here, and those two, and oops, those two, you know what I mean, and put them here, and so on. So I threw away the information at A and B because I'm only going to look at what I can say about C and D. Now, of course, the reason why this list is so long is that I haven't taken the symmetries in A, B, and C into account, because, of course, we can change things around. There's nothing special about what's called A versus B or C. So that's why I get everything repeated many times. But that's not really an issue for me, because I want to put this into a matrix, and let me show you what this matrix looks like. So essentially the idea is that the matrix has a 1 if it's possible to find a solution with these two relevant remainders modulus 13. And the way I'm making a matrix out of this might be interesting. So let me explain that in a second. That goes via map again. But first, let's get rid of this annoying thing that I'm sure you will encounter at some point. So example says that this matrix here, which is a 13 by 13 matrix, because I'm going through all the pairs of possible remainders, you can see Maple is not going to show it to me. And that's because it's sort of set up so that if something is bigger than a 10 by 10, Maple is not going to print it. And you can fix that by saying, I will let the interface be set up such that the R table size is 30. That means that now it will print a 30 by 30 matrix, and in particular a 13 by 13 matrix. But how did I create this matrix? Well, the point is that I want to write a 1 if the pair of remainders is a possibility for making a counterexample to Euler's conjecture at 3 and 4, and 0 otherwise. And I have this data telling me exactly what the C's and D's can be, but it's in this form, right? I have 0, 0, 1, 1, and so on. But now what I want to do is I want to say, okay, in my matrix, I want to write a 1 here, because this is the first row that has to do with the remainder 0, and this is the first column that has to do with the remainder 1. So how can I use the information here to put a 1 at entry 0, 0? Well, actually, the matrices are numbered not 0 to 12, but 1 to 13, so I have to add 1. But the way that I'm going to do it is I'm going to use this map thing here and make the pair 0, 0 into an equation saying that 0, 0 equals 1, or rather 1, 1, because I have to add 1 in order to satisfy the syntax of how you create a matrix in Maple. So you see, that's also done by map. And so how does that work? Well, I'm mapping the map that sends x to x1 plus 1. So it takes x is this thing here, x1 is the first entry, then I add 1 to it. That's a coordinate, that's the x coordinate of the thing I want to have a 1 at. And then the second is a 0, that extract, and I'm adding 1 to that as well. And then I make the equation saying this pair equals 1. That's of course a ridiculous statement for mathematical purposes, but the point is that this is a syntax of how you create a matrix which is sparse, in the sense that if you want to have a matrix with lots of zeros and some ones, various places, then you can make a list of the entries that you want to be 1 and put that in a set. So that's what I'm doing here, and then make that into a matrix. So this is sort of an easy way of extracting this information. And all these zeros are potentially useful because that tells me that if I have a choice of a C and D that have a 0, then there'll never be a counterexample to Euler's conjecture there. So that means that when I go through the various choices of C's and D's, then I can skip those examples. So, I mean, you can do other things like this, and I don't think I should explain everything in this little program, but essentially the idea is that I take a choice of C and D. These are potential solutions to the exercise of finding a counterexample to Euler's conjecture at fourth powers. And then I will simply go through all the possible choices of C's and D's and say, okay, if I know that there cannot possibly be A's and B's, I will skip this case. And if there is a possibility there can be an A and B, I will save this information for later. And so what's in this program is I see, for instance here, we have assumed that A and B are divisible by 5. So it's the C which is not divisible by 5. So this means that if A and B are divisible by 5, then A to the 4th plus B to the 4th is divisible by 5 to the 4th, which is 625. So if that's not the case, then I'm not going to keep this pair C and D. And then you can go through various primes, 13, 19, give something, and various other cases. And you can actually also use a deeper result by Gauss, saying that if you have a prime which is an odd prime which is not 1 modulus 8, then if that divides a sum of fourth powers, then it actually has to divide the summats. And of course, if a prime divides a fourth power, then it divides it 4 times, right? Then if p divides a to the 4, then also p to the 4 divides a to the 4 because it's a prime. So this means that when you look at a number and if you look at a potential choice of in this case the a's and the b's, then when you factorize them and you see something which is a prime which is not 1 mod 8, then it has to occur with a multiplicity which is a multiple of 4. So you can go in and do things like this and throw out potential choices of C's and D's. So the way this is going to work here, I need to run something here up. Probably just need to run this line here and this line here. So when I do this, then this is a program that goes through all possible choices of C's and D's. Right? So we know by all these considerations that there's lots of choices in C's and D's where we don't have to waste time looking for A's and B's. And now, so the idea in Frye's program, I'm going to stop this here, but is to generate all the potentially useful pairs of C's and D's. And then after that, so the idea for this is to break it over in 2 computations. So this is prepared so I can put it down in a text file. Then I can read this into Maple later and check if this choice of A's and B of C's and D's gives a corresponding choice of A's and B's. This is an exercise that I'm not going to explain, so I'm not going to say very much about it. But the point is that even though we use all these tricks that were invented by Frye and Elkies, it takes hours to do this. So I've actually done it on Maple. I'm not going to do it here because it takes too long. But still, you end up, at the end of the day, you end up being a little bit impressed by the fact that they could do this in 87. Okay, it was the fastest computer in existence at the time, but I'm sure it's not as fast as what I have on my desk right here. And so there was also some clever programming in that, I'm sure.